All right, some properties of carboxylic acids. The biggest one is hydrogen bonding. Carboxylic acids have relatively high boiling points and melting points for these molecules, and the reason is because of hydrogen bonding. They form these very interesting molecules. Okay, so you have one carboxylic acid, and then you have it hydrogen bound to another carboxylic acid. Let's see if I can draw it in here. I kind of drew this a little weird, but let's put the O here. So this is another carboxylic acid, and these are kind of how they are arranged to each other. Okay, you have these. It's kind of like a dimer. All right, you have these this dimer, meaning you have two groups. I'll put dimer. All right, you have one carboxylic acid here, the other carboxylic acid here, but they're kind of flipped to each other because of this hydrogen bonding. All right, carboxylic acids usually have a sour smell or a sour taste, like acetic acid, which is vinegar. That kind of tastes pretty bad. Foot odor, okay, and in general our BO is butanoic acid. All right, this is butanoic acid. All right, it's 4 carbons. That's what our body produces. That kind of has that little that smell to it, the foot odor, or like the gym. Like if you go into a locker room or a gym and it's got that smell to it. Everyone knows that smell. That's butanoic acid. Esters, on the other hand, actually have a pretty good smell. Most of our fruits and flowers are esters of some sort. We did the ester lab. If we haven't done it, we will do it. But it's the ester lab where we formed the winter green and the banana oil. So just to give you an example of an ester, this is kind of actually interesting. If you take butanoic acid, which smells like foot odor, and put on and make a methyl ester of it. Okay, so here's the butanoic acid, and put a methyl ester. This is the main ingredient in pineapple. So pretty interesting that our BO is very similar to pineapple. I kind of always found that humorous. In lab, we made or will make a banana oil. That is banana. Comes from acetic acid. This part of it is the acetic acid part. Everyone knows what acetic acid tastes and smells like, and just put on this group, you can change vinegar into a banana. Again, very interesting how just by doing that, you can completely change the properties, the smell, the taste, everything about that molecule. 10.3 is on acidity. Carboxylic acids are relatively acidic. The pKa's can range from 0 to 4. Remember, acidity in carboxylic acids is based on how easily the proton on the carboxylic acid can pop off. So in the presence of water, how easily does that hydrogen come off? The easier it comes off, the more acidic. So you form this ion plus H3O plus, your acid. The easier it comes off, the more acidic. Well, the ease at which this comes off is all dependent on how stable that molecule is. Okay? Well, in acids, the reason these are acidic is because of resonance of that charge. And we said that the more resonant structures you have, the more stable that charge is. Okay? So if you put in other factors in stabilizing that negative charge, it becomes more acidic. So just to kind of give you an example, let's say we take acetic acid, which has a pKa of roughly 4.8. If you put on a chlorine, if you replace one of these hydrogens with a chlorine, you now add electronegativity. And the chlorine withdraws electron away from the oxygen. Oh, I've got an oxygen there. Which stabilizes that negative charge even more, which now we have a pKa of 2.9. So notice we went down 2 pKa units. If you have 2 chlorines, called this should be a hydrogen, dichloroacetic acid, the pKa should be even more lower because your negative charge is even stabilized more. And then finally, trichloroacetic acid, pretty nasty stuff, has a pKa almost 0. It's actually 0.5. Okay, so the more stable you make that negative charge, the more acidic that ion. 10.4 now is the synthesis of acids. Pretty much we've learned actually three ways to make carboxylic acids, and we're going to learn a few more in this chapter. One way is a very specialized case by taking an sp3 carbon on an aromatic ring and adding KMnO4 to it, water, and you can hydrolyze everything that's off of it and form a carboxylic acid. That's one way. The other way we learned in the last few chapters is by oxidizing a primary alcohol with either CrO3 or Na2Cr2O7, either one, I should put or there, in the presence of acid, and you can get the carboxylic acid. Okay? A newer way is from a nitrile, which we'll talk about a little bit. With the nitrile, what you do is you hydrolyze off the nitrogen and you replace it with oxygens. The way you do that is you add sodium hydroxide, and then the second step is adding acid. And what you form is carboxylic acid plus ammonia, NH3. All right, so 1, 2, 3, 4, just to show you we have the same number of carbons. Carbons haven't vanished or anything. Basically, you're turning this carbon into a carboxylic acid. You're getting rid of that nitrogen. And basically, you're just adding these oxygens to this carbon. You're adding two. You're adding two of them. So technically, you need two equivalents of sodium hydroxide. It's not important you write that. You don't really have to write that, but just to kind of give you an idea of what's happening in the reaction. Okay? And the way that you make nitriles, this is kind of off the topic, but you make nitriles with an SN2 reaction. You add sodium cyanide. This is an SN2 reaction. Your cyanide group, just to kind of give you a mechanism, comes in, adds, kicks out your chlorine. So you are adding a carbon and you're turning it into a carboxylic acid. You don't have to turn this into a carboxylic acid. I just wanted to show you how you make nitriles. We've never seen how to make a nitrile. Well, actually, that's not true. We might have seen it on an exam or a quiz, but we've never really talked about it. But it's an SN2. Like I said, SN2 reactions can make anything, can make any functional group that you want. And this is how the quickest and easiest way is to make a nitrile.